And we have our independence, which is our 10% rule. So 10% of the first population has to be greater than the sample size of the first population. I mean the first sample. And 10% of the second population has to be greater than the second sample size. So you have to check both of them. There are some times where they don't both come into play. Like for instance, when you use the same sample but you test them 2 different times, that's a time where you wouldn't necessarily need to check it both times. We'll see a problem I think like that today. Normal. Well, there's a couple different things here. Because we're talking about counts, there's 2 different worries that we have about normal. There's, what if we know sigma? If we know sigma, then that's a z-test, or z interval. It's a z. And if n is greater than or equal to 30 for both samples, then there's no worry. You're good. It's the central limit theorem is what gets you through that. CLT is something you can use as an abbreviation on the AP test. They know what CLT is. They're just not going to know what was the reasonable to assume, RTA. They're not going to know that. Yeah. Unless you define it somewhere and then use it. But you can't define it on one page, on one problem, and then use it on all your other problems, because different people are grading different problems. So you just don't use it. Yeah, just don't use it. Thank you. Thank you for clarifying that for me. If n is less than 30, then we need to look at the graphs of the data. Unless it says that it's, if it's stated, then it's good. Look at graphs. They both have to look approximately normal. That's if we know sigma. If we're given. And if we know one, we have to know both, right? You'd have to know both of them. Well, what if we don't know sigma? If we're given Sx or S, that's your t distribution. And again, if n is greater than or equal to 30 on both samples, then you're in business. You've got the CLT, central limit theorem. But what if you don't, which is pretty common. Both graphs need to be roughly similar. They have to both kind of have the same rough shape, but they don't have to be normal. But they cannot have any outliers or any massive skew. So with no outliers or massive skew. And this is the guy that I think we're going to be dealing with most. In the last chapter, it didn't give us the option for sigma with what we were looking at, but this time it does. So you might run across it. So there are our conditions. We've got to meet the conditions. Then we have our calculations. So the confidence interval with sigma is x bar 1 minus x bar 2 plus or minus z star times. This is going to be the standard deviation for the difference of means. I'm not going to give that to you as a separate part, but know that that's what this is. This is sigma squared from the first sample over n from the first sample plus sigma squared from the second sample over n from the second sample. You will have a problem that's going to ask you to calculate either this one or the next one that I give you. Just that piece of it. That's your standard deviation. And if we go calculator shopping, which is my favorite thing to do this time of year, I've got 2 samples and I'm looking for an interval. 2 samples, z int, there it is right there. So this is going to be the shortcut to do the whole lot. You may need to break that piece out for a problem or two, but 2 samp z int. Is our second best friend. First best friend, your dog. Okay? Let's keep it in perspective, folks. Confidence interval with Sx. It's the same thing, it just uses Sx instead of sigma. X bar 1 minus x bar 2 plus or minus, oh yeah, and it changes z to t. T star times the square root of Sx squared 1 over n1 plus Sx squared 2 over n2. And the shortcut? Two samp t int. It's an interval. 2 samp t int. Actually, this is really probably going to be your best friend, and that might be your second best friend. Third, okay, second and third, right. Dog is first. Yeah, good, you were paying attention. All right, so then we conclude this kind of like we've done in the past. We are some percent confident that the true difference in means of, and you want to get some context in there, is between blank and blank. I'm going to go so far as to say that if there is no context in your answer, you haven't answered the question. Yeah.
What did you say the part under this variance?
This would be your standard error of the means, and this would be your standard deviation of the means. Yeah. Well, let's add that in. Let's see. Let me see how they note that real quick. Okay. So this they call sigma x1 minus x2 And this one would be your standard error, x1 minus x2. So I feel like that's kind of crammed in there in those notes. I hope maybe we need to do something like this. Separate, 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 separate. There we go. How's that? There, I feel better about that now. Okay. All right. Good question. Fair question there. All right, let's talk about the test for difference of means. Is everybody with me? Got it. Okay. So when we do a test, the first thing we really need to do is our null and alternative hypothesis. I kind of get a little lazy sometime, and I sometimes do that too late, but really we need to do it first. So the null hypothesis is always going to be mu sub 1 equals mu sub 2, unless you choose to write it as, not that, mu sub 1 minus mu sub 2 equals 0. The book seems to be using this second method. I frankly think it's 6 of one, half a dozen of another. I think you get. They're both hosts. They're both hosts, yes. No, there is an alternative. The alternative is going to be mu sub 1 is either greater than, less than, or not equal to, one of those three, mu sub 2. Or, if you write it the other way that the book seems to be putting it, I'm giving you this more or less because I don't want you to look in the back of the book and go, what in the hell is that? I don't know what that says. Okay? Mu sub 1 minus mu sub 2 is greater than, less than, or not equal to 0. Okay, where are you lost, Peyton? Yeah. If they're equal, when you subtract them, you're going to get 0. And if you subtract, yeah. What's that? No. The mu's are an average. That's the population mean. Right. You're comparing two populations. You're comparing two populations. Then you're still comparing them. Okay, you're comparing them. So, like for example, maybe you compare men to women from the same population, but are they really the same? You're talking different genders, so I'm gonna just shut my mouth now about men and women, and because I can already see I'm going down a bad direction. Okay, there's daggers are being shot at me. This is my way of doing it. I think it's just fine. This is the way the book's doing it. You pick. It doesn't matter to me. I think either one will work just fine. Conditions. Then you do your conditions. That's the same as the confidence interval. The ones that we just took notes on. You want alpha in there somewhere, right? Whether you set it or whether it's given. Sometimes you don't need to set it, just depends. Now our first test. If we know sigma, z equals x bar 1 minus x bar 2 minus 0. What's the minus 0 from? That's actually from this right here, right? Yeah. Over square root of sigma squared 1 over n1 plus sigma squared 2 over n2. And how many samples do I have here? 2. And what am I doing? Testing. And what am I looking to get? So I bet you this is a 2-samp Z-test, that's right.
Well, so once you get one Z value from two of these samples, does that mean there's a probability of like that happening? I don't know.
You would only get one Z when you do this,
Yeah,
okay?
once you get that one Z, what would that Z tell you?
That Z tells you how many standard deviations away from the norm, just like it always has. How many standard deviations away from the norm your difference is in this data. The norm being 0, right? Mu sub 1 minus mu sub 2, 0. That's what we expect. So it's just standardizing. It's no different than it's been. It's just a little bit more complex in terms of the formula, but you now have a nice friend there to help you out without actually doing that. So the other one, what if you don't know sigma? This is going to be the more likely scenario. It's exactly the same. We just changed the sigma for Sx and the Z for T. And this one is the 2-SAMP t-test. I'll put a little twinkle in the corner of this one because that's the good one. That's the one you'll use a lot.
Third best friend?
It's up there. It's up there. It's in your top 10 for sure.
Oh, okay.
At least right now. Okay, conclusion.
There's only one best friend.
So, the conditions and the conclusions are always the longest parts to write. If p-value is less than or equal to alpha, then we reject, right? So we're going to have a statement that says something like, we have significant evidence to reject and we're going to conclude that mu sub 1, if we're rejecting the null says that it's equal, then we're concluding that the mu sub 1 is either greater than, less than, or not equal to, it depends on what the alternative is, mu sub 2. And you need to get some context in there. Don't forget the context. However, if your p-value is greater than alpha, you fail to reject. So we say we fail to reject. And conclude there is not significant evidence to show mu sub 1 is greater than, less than, not equal to, whatever the problem is, M2. With context. degrees of freedom.
Oh, okay.
So remember, whenever we have t, we've got to calculate degrees of freedom, and degrees of freedom has always been easy. It's just n minus 1, right? Well, when we have two samples, it gets a little bit more complicated. All right. Here we go. I'm going to zoom in a little bit on that because Sx squared 1 over n1 plus Sx squared 2 over n2, quantity squared, that's just the top of the fraction, over 1 divided by n1 minus 1 times Sx squared 1 over n1 squared plus, and then the same thing with your second sample, 1 over n2 minus 1.
I'm just gonna write this out for like a simple
Mr.
math
Tatum,
problem. Looks smart.
this is sadistic right here. Whoever created this was a sadist.
And whoever created this was the opposite of a sadist. Would you agree? Okay.
They were in the also, what does it say right inside?
Wait, what did that say for that?
Which
The opposite of the same says more.
the opposite of a sadist is the person that created this thing to help us out. Yeah. Degrees of freedom for 2 samp. Yeah. Now, the good news is I don't think you'll have to calculate this. But if you do, know that I'll just say, remember, it's in your notes, I told you. Right? Okay? When you do this, when you do this, not either. When you do this, it will tell you the degrees of freedom in the answer. So if it just asks for degrees of freedom and you have enough information to put this into the calculator, that's how I'd do it. I'd say, hey, I did the test and I found that this is the degrees of freedom. So, okay, let's look at a problem. Wait, you're not done?
No, I'll just take a picture of that. Copy it later.
I wished I'd had a camera in my classrooms when I was, it'd have been awesome for art history. Because we totally would get these pictures and the guy would talk a little bit about, so we had to take notes and draw a sketch of the thing that we were being shown. What's that?
Everybody knows you don't take art history if you're not like an art major because it's hard.
And we all
It
know
is
how
hard.
this
It was one of the hardest classes I took. I would agree with that. There was a lot to know in that class. Okay, so let's look at problem 45. We're going to try to cut through 45 as quickly as we can. Although this is a bad omen. It's on page 666.
The last 4 numbers of my phone number are all 666.
My parents too. Yeah. They wanted an easy number. They got it.
That's your phone.
No, my parents' phone number has 666 in it. They asked for an easy number. They got it. An easy one to remember. Okay, so 45, we need to, thank you, sir. We need to get some stuff in the calculator. So I'm just going to put this up here and have you copy it real quick. So if you'll go into L1 and L2, put those values in. They're in the book too if you want to look there. But what we're comparing is red wine to white wine. Comparing wine in a high school class? Is that what you're doing?
What? Are you looking at me?
I don't know. I thought you said
Ethan, do you have to know?
Yeah, I did say ooh.
okay.
Is that the right? Is that the right list?
No, rate of that page? It's like the 13th floor, right?
Yes.
Okay. So what the situation is here is that they're only comparing men. I don't know really why, but basically it's one group of men. There's only 9 of them. And L1 is before they drink a half bottle of wine every night for like 2 weeks. Let's see. Let us. So either red or white wine each day for 2 weeks. The level of polyphenols in their blood was measured.
Yeah, that's not whole culture.
So I guess they're doing 2 weeks of each. So yeah, they're it's kind of nice to know that something that many people would consider a bad habit is actually maybe a good thing for your heart. What two? Negative 5.9 and 0.1. Okay, so we've got red wine versus white. And A, it says, the dot plot of the data is shown along with the summary statistics. Write a few sentences. I'm not going to write a few sentences. I'm just going to speak a few sentences about what I see here. Okay. That's number 45. So the dot plot here seems to indicate that the red wine has more of this polyphenol something in it, okay, than the white. So the lowest red is about the middle of the white count for that. That might be something you'd say about that. I don't really see any outliers. Maybe a bit of a skew on the red, perhaps. So those are some of the things I'd say. It does say construct and interpret a 90% confidence interval for the difference in the true mean percent of the poly something level. So A was me talking. B is conditions. Oh, yeah, thanks. You can't see that?
What is A?
A was me talking.
I have not seen that symbol in stats.
What?
That's a new symbol for you. Condition.
If I do that on the, can I just read that answer for a 15 symbol?
Well, yeah, why not? Why
Yes,
not?
we're kind of answering the question.
Independent. 10% of all males who drink wine is greater than 9. Can we all agree that this probably doesn't even need a reasonable to assume on this? Okay, I think this is definitely a check that one off. Normal?
Yes.
What? Normal, I'm going to quickly graph these guys. I think I've already got it set up for some box and whiskers for L1 and L2. Now I went and actually changed the colors. I made red for L1 and black for L2 because we have red and white wine. The white really didn't show up well when I tried it out. So, but unfortunately, neither does the red actually. I don't think, at least up here. So this guy here is our red wine and this is our white wine.
Do we have a standard deviation?
Not yet. I'm going to look at the box and whisker. I'm sorry, the box and whisker, the histogram. Of both, too, just for the fun of it. Do they have a similar shape? Yeah, sure. Sure, it's fine. It's good. It's good. We want this to be good so we can go forward. Okay, so no massive skew or outliers. And you probably can't see it again, right? Oh, wait, yeah, you can. Does that mean no massive outliers? Okay. All right. So we've got our conditions, and we want the 90% confidence interval. So I'm going to use the 90% confidence interval. I'm going to use the 2 SAMP T
Let's go.
int.
Yeah.
Right. 2 SAMP T int. If I go all the way down to 0, I find my 2 SAMP T int. I'm going to choose that. In this case, we have the data in the machine. So I'm going to write everything in here. List 1, L1. I'm going to call that, I'm going to say that's the red. List 2, L2, this is the white. Frequency, we leave these alone. Bless you. Confidence level 0.9 or 90%. Pooled, this is a new one. There is a thing in the book that says what pooled is, but for our intents and purposes, I wish. No. When you're asked if it's pooled, you say no. Okay?
It's not pool.
It's not pooled. So I've written down everything that I've put in. And so here is what comes out.
And the
2
frequency was
point.
1.
Yeah. That's something you don't really want to change.
I just got some clearance on the calculator.
Do a little bit of rounding here perhaps. I think I might write that all the way out if I was doing it for the AP test. And here, look what we have. DF. Yes.
Degrees of freedom.
That's what we wanted because we didn't want to do that gnarly thing. X bar 1 is 5.5. X bar 2 is about 0.23. SX1, 2.52. SX2, 3.29-ish. I don't know, after you write all that stuff down, you might think maybe it'd be shorter to put it into the formula. I don't know. But then you got to go to table A or table T and all that stuff. Yeah. It's better. So what is it that we needed out of all of that? All we needed was this thing right here, most likely. That's really all you need for the...
And that's to show you that you're 90% confident that the true mean lies between there.
The true mean difference. The true difference of means. That's what we want to say. So,
These two intervals.
yeah, we are 90% confident. Sure. The true mean difference of polyphenols. It's good stuff for your heart, they say. In red versus white wine. Is between 2.84 and 7.69. Alright, so that's it. I have one real quick extension question. Would you reject or would you fail to reject based on that confidence interval?
We would, where's the
Reject.
B
zero in the confidence interval? It's in a tail, right? You would reject.
So it's zeros.
Yeah. Zero is what we expect there to be, right? Zero is the null hypothesis.
Yeah.
Where's zero in this interval? It's not. It's going to be way out over here in the tail. So think of this as being
Okay.
zeros
Yeah,
over here.
just outside of that.
Yep. Yep. Okay. Most usually you would.